In today's lesson, we are going to be looking at applications of sinusoidal functions. So in the previous two lessons, we've looked at how to graph a sinusoidal function based off of an equation by understanding how the different values affect the base function, as well as determining an equation based off a graphical representation. So we're going to be kind of combining those two concepts or those two lessons to apply them to some real world situations. So the London Eye has a diameter of 120 meters and reaches a maximum height of 135 meters. The wheel completes one revolution every 30 minutes. We want to write an equation to define a rider's height, h, at any time, t, if the ride begins at the lowest point on the wheel. And we want to draw a quick sketch to help us with this. So I'm going to draw just a quick rough axes, and I'm going to draw a quick sketch of what this graph should look like. It does tell us that we start at the lowest point, or the ride begins at the lowest point. So I start at the bottom. Oops. So I'm going to start at the bottom. And if we think of riding a Ferris wheel, we go up to the top and back down. Up to the top and back down. Now, realistically, this probably should be the exact same graph or the exact same heights and distances because the wheel isn't changing. But again, it's just a quick sketch just so we can put some rough numbers in. So let's go back through our situation and try to place some of these values. So we know it has a diameter of 120 meters. It reaches a maximum height of 135 meters, and it completes one revolution every 30 minutes. Well, the first thing I can do is I can put a value of 135 at the top because I know that's what my maximum is. Right? It tells us that's our maximum height. We can also then figure out what's the height at the bottom because the diameter of the wheel is 120. So that means if I subtract 120, I get 15, which should be the height at the lowest point. Right? So at the lowest point on our Ferris wheel, we are 15 meters above the ground. So what else can we put in here? Well, we also do know that one revolution, or the period, is 30 minutes. So we have our rough sinusoidal function here. We want to come up with an equation for it, but is there any other information that we can kind of come up with? Is there any other information we can add to our graph? Well, we can add the midline, right? Because if I know the entire diameter is 120, the midline needs to lie 60 meters from the maximum to the midline, as well as 60 meters from the midline to the minimum. So I know my midline has to be roughly about here. And again, the reason that it's 60 above or 60 up from the minimum and 60 down from the maximum is because it's in the middle. And we know the diameter is 120. So if I go 60 down from 135, that tells us that our midline is at 75. There's no other information that we can go through and add right now, so let's try to come up with the equation. Right now, we have two options, sine or cosine. Right? Is this a sine or a cosine function? Well, we did talk about this in the previous lessons. This graph starts at a minimum. So if it starts at a minimum or a maximum, chances are we should be using cosine. So I'm going to start off h at t, so some function notation that we should have learned last year. This just means the height at any given time is equal to, and I'm going to write out just my general formula, just the basic formula, which was a cosine kx minus c plus d. That's my base function, right? And I want to go through and add any specific values I have to based off of this sketch. So h at t is equal to a, so my amplitude. Well, I do know my amplitude is 60. I got that from my graph, so I'm going to replace a with 60. Additionally, I can also add a negative. And the reason I'm adding a negative is because I start at a minimum, not a maximum. But I should recognize that cosine, or the cosine wave, usually starts at a maximum. Here it starts at a minimum, so that means it's flipped. So negative 60, still have the cosine or cos. Now k, do I have a k value? I do. And I do have a k value because the entire cycle takes less than 360 degrees. So that means there's something that's affecting or compressing my graph horizontally. So to figure out that k value, I can use the formula that we've looked at before. P equals 360 divided by k. I know P is 30. So 360 divided by something equals 30. In this case, k equals 12. So that means in my formula, I can replace k with 12. Or in other words, there are going to be 12 cycles per 360. Minus c, is there a c value that I'm missing here? Has my graph shifted left or right? There's not enough information to tell us whether it has or not. And it's a little bit too hard to tell maybe where our graph starts or where the midline reaches, like at what x value. So in this case, I'm just going to say there is no c value, right? I start at a minimum, so I haven't shifted left or right in that sense for cosine. So 12x. The last part is the plus d. How much has it moved up, or what is the midline? In this case, our midline is 75. So I'm going to add 75. So this is the equation that represents our height, or a person's height, on this Ferris wheel over any, or at any given time. So I can actually, let me take out this x and put a t. I can replace t with any time, right, from 0 to, if I'm riding it for 900 minutes. And I can use this equation to figure out the height, which is what we're going to do in part B. So we're going to go through and try to find the height at 10 and 25. So h at t equals negative 60 cosine 12t plus 75. And the first one I'm going to do 10. So h at 10, my height at 10 minutes is equal to negative 60 times cosine 12 times 10 plus 75. We get negative 60 cosine of 120 plus 75. We get h at 10. This just becomes a calculation. Make sure you do put a bracket around the 120, or if your calculator puts the first bracket in, make sure you close it, just so that we ensure that we're not doing 120 or cosine of 120 plus 75 in brackets there. We should get 105 meters. So that means at 10 minutes, our rider is 105 meters in the air. For the next one, h at 25, it's the same idea. Negative 60 cos 12t plus 75. Oops, t for right now. I'm going to replace t, though, with 25. So negative 60 cos 12 times 25 plus 75. We get h at 25 is equal to negative 60 cos 300 plus 75. This is just a calculation, and we should get that our height is 45 meters. So looking at these two values, this does make sense based off of our sketch, right? 25 minutes is close to the end of a full cycle, so we should be getting closer to 15. And at 10, we are about a third of the way through, so we should be near the top just before reaching the top. So 105 does make sense as well. So if we draw a sketch or we have a visual representation or an idea of what our scenario is, we can always use that to kind of double check if our answers make sense, right? If I had a value at 25 minutes of, say, 100, that wouldn't make sense that in 5 minutes I get to the bottom of my Ferris wheel, unless it's moving really fast, which it's not, right? Or at least in this scenario. The next one, environmentalists studied the population of wolves in a remote area of northern Ontario over a number of years and determined that the wolf population follows a 12-year cycle. At the beginning of the study, they observe a maximum wolf population of 800 wolves, and the minimum population of the wolves was 200. So the first question is, explain why a sine or cosine curve would be a good representation for the population of the wolves. Well, either sine or cosine would be good because, one, it's a cycle, right? It's going to repeat. So what they're saying is the number of wolves is cyclical. It repeats. It goes up, it goes down, it goes up, it goes down, it goes up, it goes down. And they're saying that it doesn't really tend to change or exceed certain values. And if you go back to like grade 9 science, looking at ecosystems and things like that, you might remember that there is like a carrying capacity that ecosystems have, right? You can't have too many wolves because then there's not enough food. So if the wolf population increases, they eat all the food, and then there is no food, so then the population dies off, allows the prey to come back, which allows then the wolves to come back. So it's a cyclical type situation. So that is one reason why sine or cosine would be a good representation, because it's cyclical or cyclical relationship. And secondly, if we had to decide sine or cosine, which one would be better, I would say a cosine wave or a cosine curve. And the reason I say a cosine curve would be better is because of one key piece of information in our scenario, and that is that at the beginning of the study, they observe a maximum number of wolves. And when we look at the cosine curve or cosine wave, it starts at our maximum. So a cosine curve starts at the maximum, or it could start at the minimum, right, if we flipped it. But because this starts at the maximum, it is going to be a little bit easier. We're not starting at kind of like the middle point or the midline like our sine wave. So for B, let's go through and sketch a graph similar to what we did in the previous one. I'm going to draw my axes. It tells me that, again, I start at a maximum. I'm going to just sketch it first, and I'm going to apply some of the numbers from our scenario. So it's already said that the maximum is 800 wolves. So I can put 800 here. That's our maximum. It also tells us that our minimum is 200. So our minimum is 200 wolves. So over here, it does mention a 12-year cycle. So that is essentially saying our period is 12 years, or just 12. And that's all I'll highlight the minimum population, and that's all that's really given to us in this scenario. But there is some more information that we can add. Right? Again, I know my maximum, I know my minimum. My midline needs to be somewhere in the middle. Well, not somewhere in the middle, it needs to be in exactly the middle. So if I go from 800 to 200, what is that distance? Well, 800 to 200, this entire distance, or this entire difference, is 600 wolves, or 600. So that means my amplitude has to be 300, because it's half the distance from the max to the min, or the amplitude is basically the distance from the midline to our max or min. So I know my amplitude now. I can also use that amplitude to figure out what my midline is. Because if the midline is 300 away from 800, that means it's at 500, which also makes sense because 500 is 300 away from 200, which is our minimum. So I've added all the information I can to my graph. I am going to do one small calculation because I do know what the period is. And because I'm asked to come up with an equation, I should be able to use the period to find what our K value is. So 360 divided by K equals 12. So how many 12-year cycles fit into 360? Well, we should get that K equals 30. So that is our K value. So now I can go back and I can look at, again, my base function, h, or not h this time, not height, population at time, is equal to a and cosine, because that's what I'm using, based on the fact that I'm given the maximum is where we start. So cosine kx minus c plus d. And now I'm going to go through and just add in the values that I know based off my sketch and the scenario. The amplitude I know is 300. It's not flipped because we're starting at a maximum. Right? The base function for the cosine curve starts at the maximum. So it's just going to be positive 300 because of the amplitude. Cos, I already found my K value, which is 30, because there's 30 cycles per 360, or 360 divided by 30 gives us a period of 12 years, or of 12. So 30x. Do I have a C value? Is there anything that's indicated that we are shifting it left or right? In this case, no, we don't. Right? We're told we start at a maximum, which is identical to the cosine curve. So there's nothing to indicate that we are shifting left or right. So I don't have a C value. My D value, my midline, how much did I move it up? Well, my midline is now at 500, so that's a plus 500. And this now tells me, or this is my equation, to represent or model the number of wolves. So what I can do is I can figure out how many wolves there are at any number of years. And again, this is a model. This is obviously, it may not be 100% accurate, but at least based off of the hypothetical study, it should be relatively accurate based on what they've found. So all we're going to do now is the same thing that we did in the above or the previous example, except instead of looking at height, we're looking at population. So the population at a given time is equal to 300 cosine 30x plus 500. So population at 5 years. So we're going to place t with 5. Actually, I should go back and change that. Again, you could have had px or just y equals and the x there as well. But we tend to use function notation when we have a specific scenario, just because it allows us to change some of the variables, and it's a little bit easier in terms of writing. Because p at 5 just basically means the population at year 5. So 300 cosine 30 times 5 plus 500. The population after 5 years. We have 300 cosine 150 plus 500. P at 5 is equal to 240.19. Let's double check. 240.19. So after 5 years, or 5 years into the study, we would expect 240.19 or 240 wolves in their population. So these are just applications of sinusoidal functions. Obviously, they're hypothetical, but you can see how this may come up, especially for tracking populations. Where we're looking at heights, or trying to model different relationships to make predictions. So it combines the previous lessons looking at the sine and cosine graphs and their related equations. So if you are having a little bit of difficulty understanding where we came up with these values on our graphs, please make sure you go back and review those previous lessons so you can. It helps being able to identify the key information, because once we have the graph, then it should be relatively straightforward to input those values into our equation.